And we're on. Hello everybody. So welcome back. Today we want to talk about how to get the mesh looking like this. So in order to do that, we'll need to go to our block mesh stick file. Okay. Alright, so remember in the last video we already did the extended version of the flat plate, and we found out it looks something like this. It still doesn't look quite right. And maybe you're wondering, hey, is it a problem with the fineness of the mesh? And is it because of the mesh grading? So as far as possible, we want to imitate what others have done before. We want to set up the mesh like this. Okay, so we want our mesh to be big on the left hand side for this left hand part of our block. Big on the left, small on the right. And then here it starts small on the right and big, small on the left for this right hand side block. Small on the left, big on the right. How are we going to do that? We're going to go to our block mesh stick file, and we're going to go to the blocks file. So I want you to notice this thing called simple grading. This actually contains three ratios for you. They are called expansion ratios. How does this work? How does this expansion ratio work? So for example, let's have a mesh. This is evenly divided. Okay. Let's say you have an evenly divided mesh. Okay. So you look at the first box and the last box, right? Now let's say you want this one to be bigger. You want it to be bigger, right? You want the left hand side to be bigger. So what do? You need to shrink the boxes as you go from left to right. So this is what it'll look like. You still have this line. The boxes will start to shrink as we go to the right. Okay. So expansion ratio is the ratio between this last box and then this first box. Okay. Expansion ratio equals the length of the last box and then length of the first box. So I'm using my mouse to write. Hope you don't mind. So this is, let's say, in the x direction. It goes from small x to large x. Okay, small x to large x. The expansion ratio is this length of the last box over the length of the first box. So let's just do something pretty arbitrary. We want this expansion ratio to be for the left hand side block. We'll need a small expansion ratio, so maybe we'll have 0.2. And then the expansion ratio for the right hand side, if we wanted the opposite direction, we want the last box to be 5 times the size of the first box, so that you have the small, and then you start going to, let's say the last box is a very big size. So you have a 5 times increase in size, well, we can put an expansion ratio of 5. Okay. You can even put in a expansion ratio of 6 if you'd like. Just depends. But the thing you must note, okay, for the interface, okay, I'm going to delete everything, Control A and delete. So for the interface, so remember we have the left hand side block and the right hand side block. At the interface, your mesh must be consistent. You cannot have an expansion ratio like, alright, I'll have a y expansion ratio of 3, and again you have here, you have a y expansion ratio of 5. Okay. You can't do that because this is a shared boundary. you must have the expansion ratio equal to each other. But let's say you try and do this, pull off this funny trick. Let's see what happens if you run blockmeshdict. Okay, just for demonstration purposes, you get an error. And where's the error? Okay, can you see when you run blockmeshdict, see creating block mesh from blah 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 blah. Say check topology, check block effects, creating merge list. They say foam fatal error, inconsistent point locations between 0 and 1, probably due to inconsistent grading. So that was the effect I was talking about. You have this random expansion ratios at this boundary. That is not good. You have to actually have them match each other, especially at the boundary. So CD system, okay, we'll go to blockmeshdict. We'll need to change our expansion ratios to be equal. So if I want that to be 5 there, I'll have to have a 5 here as well. But for the X side, it probably does not have this kind of restriction, so I don't need to have an expansion ratio of 0.2, and then the other side I would have think, oh okay, maybe I need an expansion ratio of 1 over 0.2, then I need an expansion ratio of 5. So just for demonstration purposes, I'm going to leave it as 6 to see whether it's really true, and we need to do it like so. So we're going to do a run. Okay, so it's going to run very nicely. Okay, now I want you to notice something in this this Courant number. You never ever are supposed to exceed 1 for this Courant number. Okay, what is the Courant number? Okay, let's search online. Okay, Courant number is as such. Okay, never mind, I'll just draw it here. Let's say you have a box, and then you have fluids flowing at velocity u, and this box has a length L. Okay, so you can see something like this. Okay, we'll go to Wikipedia. So you see? Alright, so let's say if you have the time u, the velocity u, and your time step is t. Okay, that means the fluid actually travels this certain distance, u delta t. Now if your Courant number is defined as the ratio of this u delta t, which is the time step, over L, which is the size of the mesh. So basically, your fluid has traveled more than one box. If the Courant number is, let's say, 1.2, it has traveled 1.2 boxes ahead. So that's not a good thing, because you have basically skipped a box and you don't give the code enough time to calculate. So Courant number, rule of thumb, it should always be less than 1. And then there may be other kinds of Courant numbers restrictions. Okay, and yeah, the maximum is 1. Okay, so we don't want it more than 1, so we'll have to change something. Okay, so let's go to system and change the time step. And we see that the max Courant number is 12.4. Okay, if the max Courant number is 12.4, we'll want to divide it 12.4 times or 12.45 times. Well, we can round it up to like 20. Okay, so let's go to control dict. Okay, and then we'll have this delta t 0.005, and then we want to divide it by 20. Equals 0.005 divided by 20. So 00025. Okay, so 00025. That's appropriate. And then we want the right interval. Okay, so this is going to write for every time step, but since we have increased the time step by 20 times, I'm going to multiply this by 20 so that we all have the same results. Okay, so if we have 20 time steps, that means we'll have 20 times the number of files output. I don't want so many output files, so I'm just going to change the time step. Okay, so yeah, that's the Courant number. I think you can yeah, I think there's actually a special way that you can tell the code to stop running if it exceeds a certain Courant number. It's over here in this 6.1. Okay, I can put this in the link again. Okay, I'm going to put it here, Courant number control. Use this link. Okay, so that's a useful thing to know, that if you want to stop your code running at a certain Courant number, you can, I think you can just write a max Courant number. So I'm just going to insert max Courant. Okay, max co. Okay, it's like that. I hope this works. So the max Courant number is always 1, never exceeding 1. Okay. Okay, let's see what happens when I just change that. We want to test whether that works, right? So if you're going to use our old time step, then our program should stop. Okay. Okay, so I'm going to run. Okay, it looks like our Courant number is exceeded. Maybe it doesn't work here. Oh, I'm not that sure how to write. Never mind, forget it. We'll just do an all clean again. Next time I can go and try to figure that out. It's an interesting, convenient thing. But anyway, let's go to system. VI block mesh dict. Oh, wrong one. Control dict. Okay. Oops. Okay, never mind. There you go. We'll just put the 00025. Okay, 025. Here's our time step. Okay. And we're gonna do a run. And let it. Okay. Now, look at this. Our current number is very good, but it says there's a foam fatal error. Continuity error cannot be removed by adjusting the outflow. Basically, the initial guess is a bit too far from the initial guess of velocity. So remember, our velocity field was 1 meter per second throughout. That's our initial velocity guess. Okay. But yeah, now that you're forcing the flow in, especially with a smaller mesh size at the center and here, OpenFoam's gonna scratch his head. It's like, what's going on? We can't adjust the outflow, so to speak. I mean, the initial guess of velocity here is maybe too far from the actual, velocity that you're trying to guess. Yeah, so that kind of gets an error. So if the initial velocity over here, the guess is 0 meter per second, right? And let's say in one of these cubes, let's say here, okay, you have a very large influx of velocity here, but the velocity here, here, and here, these are all 0. Then OpenFoam is going to wonder, which file is it, which 0 is it going to adjust? So this is the concept. It's not exactly the case, but that's what's going on. So the idea is to have an initial velocity field. So they ask us to run potential foam, but I'm not going to do that. I'm just going to do something very much simpler. Okay. Again, if you look at the site, this website where we get this guy from. Okay, OpenFoam net Blasius flow benchmark. Now that actually tells us to have a velocity field of 1. Okay, say time can be saved by setting the internal field to a uniform of 0.200. So his initial velocity is 0.2. Okay, so we want to change our initial velocity inside this velocity field of the initial velocity field, which is here, VIU. So internal field, that will tell us the uniform velocity field. We'll just want to change it to 1. That will solve our problem. Okay. Okay, then we're going to type run. And that should be able to solve our problem. Now you see that the time step has been 20 times shorter, so we will have way more calculations, and it's gonna get a bit messy. You see, I can just stop this. It will still run in the background, but this is for us to look at. So for the same amount of time, okay, you'll be 20 times slower. You're only at 0.16 seconds. So I see. It became 0.2 something just now. So we're gonna wait for a while. Okay. And if you don't like this pattern, you can always run it in the background. So we can save all these as a log, and then you don't have to worry about it. So we can always run in the background. Okay. But before we continue, since we have this already, okay. Since we have this already, I'm just going to rename it flat plate extended graded foam. Okay, I'm just going to move it over since we have results. But yeah, I just want to compare with the Paraview very quickly. Yeah, but we can of course compress the output to something more convenient. Let's say we want to suppress this output, and then we just tell it, oh, OpenFoam, put everything here in a log file. Yeah, we can do that. We can just change a little code. But we'll want to see this first because it's interesting to see. Okay. Apply. Okay. Let's see. Okay, so the pressure scale is as such, similar kind of a thing, and we notice our U. Okay, so we have a lot more high resolution, but it's still high resolution of the wrong thing. You want to see our mesh? This is what our mesh looked like. You see, we take this block U rather than this circle. This one's a continuous looking thing. This one will show us the mesh. So you see, when we get the expansion ratio right, this is what will result. Okay, it gives us a very high definition kind of a picture while using the similar computation time, except that it only increases because of the time step. Okay, rather than we increase the number of meshes to solve. So apparently, yeah, at least we got the grading right, and that's something for us to learn. But we still got this. We don't get the boundary layer flow that we really want. We're going to wonder what's going on. Okay, so in the next video, we'll explore some other things. We know that the mesh size and the time step are just about right because the Courant number is pretty low. We have refined the mesh. We have even given it the entrance region that was consistent with what was online. So what's wrong? We'll find out more. We'll look at other possibilities in the next video. We'll see what else we can learn about improving our code to make it more efficient to run, or rather suppress the output, you know. Okay, so I'll see you guys in the next video. Thanks for watching.